Linear Algebra II, Tutorial 7, Eigenvectors and Eigenvalues. Problem 1. Determine all eigenvalues and the corresponding eigenvectors for the linear operator f from R3 to R3, given in the standard basis by the following matrix: 2, 0, minus 1, 0, 2, minus 1, 2, 2, 2. Solution. Each problem for eigenvalues and eigenvectors is reasonable to start by computing the characteristic polynomial of the linear operator. This characteristic polynomial is the determinant of the matrix which we obtain when we take the matrix of our linear operator and subtract minus x on the main diagonal. So we need to compute the determinant of the matrix 2 minus x, 0 minus 1, 0 to minus x minus 1, 2, 2, 2 minus x. So this is equal to 2 minus x cubed plus 0 minus 1 times 2 minus x, so plus 2 times 2 minus x, plus 0, and again minus 1 times 2 minus x, plus 2 times 2 minus x one more time. So put together we can take out 2 minus x, we will get 2 minus x times 2 minus x squared plus 4. So this quadratic polynomial is equal to x squared minus 4x plus 8. Because 4 squared, which is 16, minus 4 times 1 times 8, so minus 32, this is a negative number. This quadratic polynomial does not have any real roots. Therefore, the only real root of this cubic characteristic polynomial is x is equal to 2, so lambda 1 is equal to 2, and the algebraic multiplicity of this root is 1. So we have only one real eigenvalue, lambda 1 is equal to 2, and the algebraic multiplicity of this eigenvalue is 1. Note that if we would have worked over the complex numbers, we would have two more complex eigenvalues. But we work over the real numbers, so we have only one real eigenvalue. Let us determine the eigenvectors for this real eigenvalue. So the eigenvectors for the eigenvalue 2 are the solutions to the homogeneous system of linear equations which we obtain, where we take the matrix of our linear operator, subtract the eigenvalue on the main diagonal, and look at what we get. So we get the matrix 0, 0, minus 1, 0, 0, minus 1, 2, 2, 0. So here we have the first two rows are the same, so we can delete one of them. We multiply the next one by minus 1 to get 0, 0, 1. And 2 to 0 we can divide by 2. So we get the matrix 1, 1, 0, 0, 0, 1. So here we have leading elements in columns 1 and 3, so we can take x2 as a free variable. From the first equation we have x1 is equal to minus x2. For the free variable we have the trivial equation x2 is equal to x2. And from the second equation we have x3 is equal to 0. So in the vector form, x1, x2, x3 is equal to x2 times the coefficient vector minus 1, 1, 0. So this means that the vector minus 1, 1, 0 forms a basis in the linear space of solutions to this homogeneous system of linear equations. And so this vector minus 1, 1, 0 forms a basis in the space of all eigenvectors for f with eigenvalue 2. So we have only one eigenvector and only one eigenvalue, so our operator f is not diagonalizable. So this is a remark. Problem 2. The linear operator g from R3 to R3 is given in the standard basis by the following matrix: 2, 1, 2, a2, a minus 3, 1, minus 1, 1. So here a is a real parameter. Determine for which values of this real parameter a the linear operator g is diagonalizable, and for each such value of a, determine the diagonal form of G and the corresponding basis of eigenvectors. Solution. As usual, we start by computing the characteristic polynomial. So we need to compute the determinant of the matrix, which we obtain when we take the matrix of our linear operator and subtract x on the main diagonal. So we have the matrix 2 minus x, 1, 2, a, 2 minus x, a minus 3, 1 minus 1, 1 minus x. So this determinant is equal to 2 minus x times 2 minus x times 1 minus x, the first summand, plus a minus 3, minus this one 2a, minus 2 times 2 minus x, plus, because of this, so minus 1 times a minus 3 times 2 minus x, so plus a minus 3 times 2 minus x, and finally minus a times 1 minus x. So when one computes all this expression, one gets minus x to the power 3 plus 5x squared minus 3x minus 9. So if this to have integral roots, they would be plus minus 1, plus minus 3, or plus minus 9. And we can readily see that minus 1 is a root. So then we can divide by x plus 1 and then see what we get as the quadratic equation and solve that quadratic equation, or simply check that also 3 is a root, and then when you take out x plus 1 and x minus 3, what remains is x minus 3. So this cubic polynomial is equal to minus x plus 1 times x minus 3 squared. So we have two different eigenvalues. The eigenvalue lambda 1, which is equal to minus 1, with algebraic multiplicity 1, and the eigenvalue lambda 2, which is equal to 3, with algebraic multiplicity 2. Since the algebraic multiplicity of minus 1 is 1, its geometric multiplicity is also 1 automatically. So for diagonalizability, we need to determine the geometric multiplicity of the eigenvalue 3. There are two possibilities. It might be either 1 or 2. If it is 1, then the linear operator is not diagonalizable. And if it is 2, then the linear operator is diagonalizable. So the eigenvectors for the eigenvalue 3 are the solutions to the homogeneous system of linear equations which we get when we take our matrix and subtract 3 on the main diagonal. So we get the matrix minus 1, 1, 2, a minus 1, a minus 3, 1, minus 1, minus 2. Here we see that row 1 and row 3 are linearly dependent, so we delete row 1 and put row 3 as row 1. So we get 1 minus 1 minus 2, a minus 1, a minus 3. So now we multiply the first row with minus a and add to the second row. The first row remains the same, 1 minus 1 minus 2, and the second row becomes a minus a is 0, minus 1 minus 1 times a is minus 1 plus a, and a minus 3 minus 2 times a, which is 3a minus 3. If a is not equal to 1, we can divide the second row by a minus 1 to get the matrix 1 minus 1 minus 2, 0, 1, 3. This is a row echelon matrix with leading elements in columns 1 and 2. In particular, it has rank 2. And hence our system has the number of variables, which is 3, minus rank, which is 2. So we get 1. Our system has one linearly independent solution. This means that the geometric multiplicity of 3 is equal to 1, which is not equal to 2, that is the algebraic multiplicity of 3. So for such values of a, namely if a is not equal to 1, the linear operator G is not diagonalizable. If a is equal to 1, then we get the matrix 1 minus 1 minus 2. This matrix has rank 1, and hence the corresponding system has two linearly independent solutions. 3 variables minus rank 1, which is equal to 2. Two linearly independent solutions. Therefore, the geometric multiplicity of 3, which is equal to 2, equals the algebraic multiplicity of 3, which is 2. So we have that the geometric multiplicity of each eigenvalue is equal to the algebraic multiplicity of each eigenvalue, and the sum of all these multiplicities is the degree of the characteristic polynomial. Therefore, in this case, that is for a is equal to 1, the linear operator G is diagonalizable. So let us determine now the eigenvectors. Here we have a row echelon matrix with leading element in column 1. So we can take x2 and x3 as free variables. From the equation we get x1 is equal to x2 plus 2x3. For the free variables we have the trivial equations x2 is equal to x2 and x3 is equal to x3. In the vector form, x1, x2, x3 is equal to x2 times the coefficients 1, 1, 0, plus x3 times the coefficients 2, 0, 1. Therefore, we have that the coefficient vectors 1, 1, 0 and 2, 0, 1 form a basis in the subspace of all eigenvectors for G with eigenvalue 3. Now let us determine the eigenvectors with eigenvalue -1. These are the solutions to the homogeneous system of linear equations, which we get when we take the matrix of our linear operator and subtract -1 on the main diagonal. So we get the matrix 3, 1, 2, 1, 3, -2, 1, -1, 2. So we swap the first and the third rows and use this 1, which we now have in position 1, 1, to kill all other elements in its column. So the first row remains the same, 1, -1, 2. We subtract the first row from the second row. We get 1 -1, which is 0, 3 minus -1, which is 4, -2 -2, which is -4. And then we subtract 3 times the first row from the last row. So we get 3 minus 3, 0, 1 plus 3, 4, 2 minus 6 is -4. And now we see that rows 2 and 3 are the same. We delete row 3 and we divide row 2 by 4. So we get the matrix 1, -1, 2, 0, 1, -1. And now we can use this 1 to kill this -1. We add row 2 to row 1. So we get 1, 0, 1, 0, 1, -1. Now we have a row echelon form with leading elements in column 1 and 2. So we take x3 as a free variable, and from the first row we have x1 is equal to -x3. From the second row we have x2 is equal to x3, and for the free variable we have x3 which is equal to x3. In the vector form, x1, x2, x3 is equal to x3 times -1, 1, 1. Therefore, the vector -1, 1, 1 forms a basis in the subspace of all eigenvectors for G with eigenvalue -1. Now we can write down the answer. So the diagonal form consists of our eigenvalues written with multiplicities. So it's a diagonal matrix with 3, 3, and -1 on the main diagonal. And the transformation matrix consists of our linearly independent eigenvectors. So in the diagonal form, the first two elements on the diagonals are 3. So the first and the second column of the transformation matrix should contain eigenvectors for this eigenvalue. So these were 1, 1, 0 and 2, 0, 1. In the diagonal form, the third element on the diagonal is -1. So the third column in the transformation matrix contains the linearly independent eigenvector for the eigenvalue -1, which is -1, 1, 1. And this completes problem number 2. Problem 3. Compute a to the power 100, where a is the matrix -2, -2, 1, 1. Solution. We observe that it is very easy to compute powers of diagonal matrices. If we have a diagonal matrix with lambda 1 and so on lambda n on the main diagonal, then this diagonal matrix to the power 100 is a diagonal matrix again, now with lambda 1 to the power 100, lambda 2 to the power 100, and so on the main diagonal. So if we can reduce our matrix A to the diagonal form, that is, if we can write that A is equal to some transformation matrix times the diagonal form times the inverse of the transformation matrix, then A to the power 100 would be the transformation matrix times the diagonal matrix to the power 100, which we can compute, times T inverse. So let us see whether A is diagonalizable, and if yes, let us determine D and T. To start with, let's compute the characteristic polynomial of A. It's a determinant of the matrix when we take the matrix A and subtract x on the main diagonal. So we have minus 2 minus x, minus 2, 1, 1 minus x. So this gives us minus 2 minus x times 1 minus x plus 2, which is x squared plus x. So it is x times x plus 1. So we have two eigenvalues. Lambda 1 is equal to 0 with algebraic multiplicity 1, and lambda 2 is equal to minus 1 with algebraic multiplicity 1. So the geometric multiplicity must be 1 in both cases, and so this matrix is diagonalizable. Let us compute the eigenvectors. For the eigenvalue 0, these are the solutions to the homogeneous system of linear equations, with the matrix being the matrix of our linear operator. So we see that the rows are linearly dependent. We can delete row 1 and get the matrix 1, 1. So here we can take x2 as a free variable. From our equation, we have x1 is equal to minus x2, and x2 is equal to x2. This is the equation for the free variable. So in the vector form, x1, x2 is equal to x2 times minus 1, 1. Therefore, the vector minus 1, 1 is a basis of the subspace of all eigenvectors for A with eigenvalue 0. Now the eigenvectors for A with eigenvalue minus 1 are the solutions to the homogeneous system of linear equations when we take our matrix and subtract minus 1 on the main diagonal. So we get the matrix minus 1, minus 2, 1, 2. Again, both rows are linearly dependent. We delete row 1. We get the matrix 1, 2. This is row echelon form with leading element in column 1. So we take x2 as a free variable. From our equation, we have x1 is equal to minus 2x2. Then for the free variable, we have the trivial equation x2 is equal to x2. In the vector form, x1, x2 is equal to x2 times minus 2, 1. Therefore, the vector v2, which is equal to minus 2, 1, forms a basis in the linear space of all eigenvectors for A with eigenvalue minus 1. So the diagonal form is a diagonal matrix with our eigenvalues 0 and minus 1 on the main diagonal. And the transformation matrix has as the first vector the vector minus 1, 1, which is the eigenvector for the eigenvalue 0, which is the first diagonal element. And the second column in the transformation matrix is minus 2, 1, which is the eigenvector for the eigenvalue minus 1, which is the second diagonal element. As a next step, so we now have the transformation matrix, but we also need the inverse of the transformation matrix for the computation. So we find the inverse of the transformation matrix. For this, we write down our transformation matrix, and then the vertical line, and then the identity matrix, and we reduce the transformation matrix to the identity matrix using Gauss elimination. So here what we can do, we can swap the two rows and add row 2 to row 1. So row 2 becomes row 1, and row 2 becomes 1 plus minus 1, which is 0. 1 plus minus 2 is minus 1, and then 1 plus 0 is 1, 1 plus 0 is 1. So now we multiply row 2 by minus 1 to get 0, 1, minus 1, minus 1. And now we subtract row 2 from row 1. So we get the matrix 1, 0, 1, 2, 0, 1, minus 1, minus 2. So the inverse of our transformation matrix is the matrix 1, 2, minus 1, minus 1. And now we compute A to the power 100. So this is equal to TD T inverse to the power 100, which is equal to t, d to the power 100 t inverse. So t is minus 1 minus 2, 1, 1. D to the power 100, so the matrix D was the diagonal matrix with 0 and minus 1 on the main diagonal. So 0 to the power 100 is 0. Minus 1 to the power 100 is 1. So in the middle we have the matrix 0, 0, 0, 1. And T inverse, we just computed 1, 2, minus 1, minus 1. So we multiply the first two matrices, we get 0, minus 2 times 0, 1. So 0, minus 2, 0, 1 times the last matrix 1, 2, minus 1, minus 1. And when we compute, we get 2, 2, minus 1, minus 1. So the matrix A to the power 100 is equal to 2, 2, minus 1, minus 1. And this completes problem 3. Problem 4. Diagonalize in an orthonormal basis the symmetric operator f from E4 to E4, which is given in the standard basis by the following matrix: 1, 2, 2, 1, 2, 1, 1, 2, 2, 1, 1, 2, 1, 2, 2, 1. So this is a symmetric matrix. The standard basis is an ONB, so a symmetric matrix describes a symmetric linear operator in an ONB. Solution: we always start by computing the characteristic polynomial. So we take our matrix, subtract x on the main diagonal, and compute the determinant. So here it's very useful to observe that the sum of all elements in each column is the same. It's 6. 1 plus 2 plus 2 plus 1 is 6. 2 plus 1 plus 1 plus 2 is 6, and so on. In this case, we add all rows of our matrix to row 1. And then row 1 becomes 6 minus x, 6 minus x, 6 minus x, 6 minus x. And then we can take out the 6 minus x from row 1, and the row 1 becomes 1, 1, 1, 1. So now we can use this 1 in position 1, 1 to kill 2, 2, and 1 in the first column. This doesn't affect the determinant. So we subtract row 1 from row 4, and we subtract twice row 1 from rows 2 and 3. So we get 6 minus x times the determinant of the matrix 1, 1, 1, 1, 0, minus 1 minus x, minus 1, 0, 0, minus 1, minus 1 minus x, 0, 0, 1, 1, minus x. And we see that this is a block upper triangular matrix, where one block is just 1, and the other block is this 3 times 3 matrix. And the 3 times 3 matrix is in turn block lower triangular with a block minus x and this 2 times 2 matrix. So this determinant is equal to 6 minus x times minus x times the determinant of the 2 times 2 matrix minus 1 minus x minus 1 minus 1 minus 1 minus x. So this is equal to 6 minus x times 1 plus x squared minus 1, which is x squared times 2 plus x times x minus 6. So we have 3 eigenvalues. The eigenvalue lambda 1, which is equal to 0 with algebraic multiplicity 2. The eigenvalue lambda 2, which is equal to minus 2 with algebraic multiplicity 1. And the eigenvalue lambda 3 equal to 6 with algebraic multiplicity 1. The eigenvectors for the eigenvalue lambda 1 equal to 0 are the solutions to the homogeneous system of linear equations whose matrix is just the matrix of our linear operator. Since the eigenvalue is 0, nothing to subtract on the main diagonal. So here we readily see that rows 1 and 4 are the same, and rows 2 and 3 are the same. So we can delete rows 3 and 4 to get the matrix 1, 2, 2, 1, 2, 1, 1, 2. So now we subtract twice the first row from the second row to kill this 2. And then we will get the matrix 0, minus 3, minus 3, 0. So we divide the second row by minus 3 to get 0, 1, 1, 0. And then we subtract twice that from the first row to get 1, 0, 0, 1. So this is the row echelon form 1, 0, 0, 1, 0, 1, 1, 0. And one can do the usual thing how you find solutions or directly guess them here. So the vectors 1, 0, 0, minus 1 and 0, 1, minus 1, 0 form a basis in the vector space of all solutions to this linear system, that is, in the vector space of all eigenvectors for f with eigenvalue 0. Please note that v1 is orthogonal to v2. We got lucky in this situation. So we only need to norm them. So they have lengths root of 2. So the vectors w1, which is 1 divided by the root of 2, 1, 0, 0, minus 1, and w2, which is 1 divided by the root of 2, 0, 1, minus 1, 0, they form an ONB in the space of eigenvectors with eigenvalue 0. Next, we need to compute the eigenvectors for the eigenvalue minus 2. So we take the matrix of our linear operator, subtract minus 2 on the main diagonal, and we need to solve this homogeneous system of linear equations with this matrix. So after the Gauss elimination, this reduces to the matrix 1, 0, 0, minus 1, 0, 1, 0, 1, 0, 0, 1, 1. And the homogeneous system of linear equations with this matrix has one linearly independent solution, which is a vector 1, minus 1, minus 1, 1. So this vector has lengths 2. Therefore, when we norm it, we get that the vector 1 half, 1 minus 1 minus 1, 1, which we denote by W3, forms an orthonormal basis in the subspace of all eigenvectors for f with eigenvalue minus 2. Finally, we need to determine the eigenvectors for the eigenvalue 6. These are the solutions to the homogeneous system of linear equations with the matrix which we get when we take the matrix of our linear operator and subtract 6 on the main diagonal. Using Gauss elimination, this reduces to the matrix 1, 0, 0, minus 1, 0, 1, 0, minus 1, 0, 0, 1, minus 1. Hence, the vector 1, 1, 1, 1 is a basis in the space of solutions to this homogeneous system of linear equations, that is, in the space of eigenvectors of f with eigenvalue 6. It has lengths 2, which means that if we norm it, the vector w4, which is 1 half of 1, 1, 1, 1, forms an orthonormal basis in the subspace of all eigenvectors for f with eigenvalue 6. And here is our answer. So the diagonal form consists of the eigenvalues on the diagonal. So we have the diagonal matrix with eigenvalues on the diagonal. So these are 0, 0, minus 2, and 6. And for the transformation matrix, we write the corresponding eigenvectors as columns. So we have the first two diagonal elements in the diagonal form are zeros. So the first two columns should be the eigenvectors for the eigenvalue 0. So these were minus 1 divided by the root of 2, 0, 0, 1 divided by the root of 2, and 0 minus 1 divided by root of 2, 1 divided by root of 2, 0. But there was a coefficient 1 divided by 2 in other eigenvectors. If we take it out of the matrix, the first two columns become minus root of 2, 0, 0, root of 2, 0, minus root of 2, root of 2, 0. Now, the third diagonal element is minus 2, so the third column is the eigenvector for minus 2, which is 1 half, minus 1 half, minus 1 half, 1 half. And the last column is the eigenvector for 6, which is 1 half, 1 half, 1 half, 1 half. So this is the transformation matrix. And this completes problem 4. Some other problems and questions. Question 1. Determine all eigenvalues and the corresponding eigenvectors for the linear operator f from Rx3 to Rx3 given by f of x goes to x plus 2 times f prime of x. Question 2. The linear operator g from v to v is non-zero and satisfies g to the power 3 is equal to 0. Is g diagonalizable? Question 3. Prove that the 49th power of the matrix 3, 3 minus 4 minus 4 is equal to 3, 3 minus 4 minus 4. Question 4. Compute 2, 1, 1, 2 to the power 200. Question 5. Diagonalize in an orthonormal basis the symmetric operator f from E3 to E3, which is given in the standard basis by the matrix 3 to 1, 2 to 2, 1 to 3. Thank you very much and see you next time.